Yes.
Okay, good. So good afternoon, everyone. Thank you for taking your time to attend this webinar. And I hope everyone stay safe and healthy and continue to do so during this unprecedented time. And my name is Wei Fan. I'm a professor of Civil and Environmental Engineering Department here at University of North Carolina at Charlotte. I'm also the director of Kamsi University Transportation Center. We're glad to host the webinar on developing a systematic method for identifying, ranking, examining, and mitigating freeway bottleneck. This webinar is hosted by Kamsi. So speaking of Kamsi, I'm assuming that not everyone, not each and every one of you know Kamsi. So I'm going to take a few seconds to give you a little bit of background information about our center. So Kamsi stands for Center for Advanced Multimodal Mobility Solution and Education. This is a multiple-year, multi-campus, Tier 1 University Transportation Center, funded by U.S. Department of Transportation under the FAST Act. So we're a consortium of 5 universities. As you can see the map here, we are spread across the country, led by us here at UNC Charlotte. We are proud to have University of Texas at Austin, University of Connecticut, Washington State University, and Texas Southern University as our partner institutions. And the outline of my presentation today is organized as follows. I'm going to talk about the introduction first, so give you some background information about the topic we're going to be presenting today. And then I'm going to discuss the needs for research, and then describe the research goals and objectives, and also share with you some of the results of the literature review. And we're going to present the methodology and numerical results. And also we're going to talk about the contributions of our research and also the technology transfer activities that already are going on here at our center. And here's the introduction slides. As we all know, the highway demand continues to grow all across the nation and also around the world. Pretty much everywhere, from urban to suburban to rural areas, from large cities to small cities. As we all know, the highway capacity cannot catch up with the demand. And some research shows already we cannot simply build our way out of a congestion. And even that's not the case. Let's assume that's not the case. We have we're still running into the funding issue. As we all know, since 1992, the 18.4 cents per gallon, that gas tax funding mechanism has never been changed since 1992. And over the years, we have a lot of inflations, and also the new technologies like the electric vehicles. All those will reduce the transportation funding. So all those factors combined, so we cannot just simply add new roads and construct, build a lot of constructions of new roads. So we cannot simply do that. And Cambridge Systematic and Texas Transportation Institute conducted research back in 2004 and told us that nearly 40% of the congestion nationwide can be attributed to the physical bottleneck. And 5% or so can be attributed to the signal coordination. So those these two combined, we have a 45% or so due to the the fact that we do not have enough capacity. The other 55% coming from the temporary, like accident, work zones, and weather-related issues. So as you can see clearly, that mitigation of a bottleneck is a top priority. So how to mitigate bottleneck requires basic information about where the bottleneck exactly located and how far are they, from where to where, from when to when, and information like that. We needed to know, to get perfect information about bottlenecks. And there are a lot of challenges that we are facing in terms of improving bottleneck analysis. The first one, as you can see here, is data. So data, historically, we kind of like place the loop detectors underneath the pavement, so we can collect the data, and we can develop a data analytics approach, to see where bottlenecks are, and then go from there. So data is an issue because loop detector, essentially is limited in coverage. The second issue is performance measures. So historically, we use the volume over capacity ratios, and also the level of surfaces, and all those are becoming outdated at this point. And the Federal Highway Administration recommends the incorporation of travel time reliability measures into the congestion analysis process. And the third one mainly comes from the modeling perspective. As we all know, the operational model lacks regional scope. For example, those models pretty much are macroscopic in nature. You can see the cars, got simulated across the network, but we cannot model the large scale network. On the other hand, for the planning model, we cannot capture traffic dynamics. So that's coming from the macroscopic perspective. That's also a big issue as well. So we do need to develop a systematic approach to improving bottleneck analysis at the network level. And the primary goal of this research is to develop a systematic approach to holistically identifying, ranking, examining, modeling, and mitigating bottleneck at the network level. So we developed several objectives in order to achieve the goal. The first one is to conduct literature review, and then we will define a set of measures of effectiveness for freeway bottleneck analysis. Now we're going to develop a systematic approach to identifying and ranking bottlenecks. And then we develop the DTA-based models for analysis, for analyzing the bottlenecks, and also ranking the bottlenecks as well. So here it comes to the literature review section. So the first one is bottleneck definition. So Chen, etc., those authors in 2004, they defined bottlenecks as a freeway segment that routinely experience traffic congestion during peak periods. The root cause, obviously, is the imbalance between the demand and the capacity. So historically, the bottlenecks can be classified into different categories, depending upon which angles, which perspective you're looking at the same issue. For example, the first one, some people classify the bottlenecks into two categories: recurrent versus non-recurrent bottlenecks. So recurrent basically talking about, for example, when we commute to work early in the morning, we get to the same point, maybe we experience same level of congestion from day to day. At same point, we are experiencing congestion. That's called a recurrent. So non-recurrent basically deal with the weather, work zone, and also accident-related bottlenecks. Then the second category is moving versus stationary bottleneck. So moving bottleneck, we're talking about scenarios like this. More often you can see when you're driving on the freeway, you see a big truck, slow moving, but you have a platoon of fast moving passenger cars following a slow moving truck. So in situation like this, we have a moving bottleneck, defined by the slow moving trucks. And then we have a stationary bottleneck. For example, the bottleneck is there, it's stationary, it's not moving. The third category is active versus inactive and hidden bottleneck. So active bottleneck, we're talking about, the bottleneck is there. You can see that. The inactive, so sometimes when we mitigate the bottlenecks, so we develop some countermeasures, and we, for example, construct more roads, adding more lanes. Initially, the active bottlenecks will be gone. Initially, the inactive and hidden bottlenecks, they will emerge as new bottlenecks. So often we can see that. That's another classification method. And in terms of common locations bottlenecks, we often see that when we have a lane drop scenario. For example, you have 4 lanes, drop to 3 lanes, we have lane deduction. Then we can easily see the bottleneck exist under those situations. The second one is talking about weaving. So weaving segment. So some vehicles are trying to get off the freeways. Some others trying to get onto the freeways. When they weaving segment are short, so we can see the bottleneck exist. And then the third category is on and off ramps. So when we have those, I'm sure that when you commute or conduct some other activities, you can easily see that as well. So interchanges also. And we're talking about also horizontal curves and vertical curves. So when we have sharp horizontal curves, also steep gradient, and also tunnels, underpasses, and narrow lanes. So those are the situations we're going to see bottleneck right there. And then we conduct the literature review for the bottleneck identification method. So the literature here, we're including in this and the next slides as well. We're not trying to show all the paper review, but we're trying to just give you an idea of what's going on, what has been done in the past. So the Cambridge systematic conducted in 2005 made an effort to locate bottlenecks using the highway performance monitoring system database and also use the volume over capacity ratios. Chen, back in 2004, developed an approach to automatically identifying freeway bottleneck using 5 minutes speed data collected from loop detectors. And they declared bottleneck when the upstream speed drops below 40 miles per hour and downstream traffic it's like 20 miles faster than upstream traffic. So they use the absolute value of the speed. On the other hand, Florida DOT conducted a study in 2011 using their database. So they declared the roadway are congested when the average speed drops below 75% of the free flow speed, or the planning travel index is greater than the predefined threshold. However, it's unclear how they combine these two in their study. And then another study conducted in 2014 in Maryland, they use both travel time index and also planning time index. For example, they classify the roadways are congested when the TTI, which is travel time index, is greater than 1.15. So they and congested, light, heavy, and severe congestion classified. In terms of trip reliability, so when the travel time index less than 1.5, they classify as reliable. On other side of the spectrum, basically when the PDI is greater than 2.5, they think the roadways are extremely unreliable. So this table basically gives a summary of a bottleneck identification method using loop sensors, local sensors. And then these slides basically used vehicle probe data to identify bottlenecks. As you can see here, we classified by data types, data aggregation level, data sources, and also study periods and what congestion index have been used in the past. Again, this list is not trying to be exhaustive. Rather, we're trying to give you a picture, an idea of what's going on in the past. They are very representative. We think of the very good papers or reports as a great starting point. That's the point here, okay. So these slides basically give you a summary of a previous bottleneck identification method using local sensors and vehicle probe data. So using local sensors mainly for operational applications, they're limited in data coverage. On the other hand, for vehicle probe data related research, mainly used for planning purpose, they can account for multiple dimensions of traffic congestions. For example, intensity, reliability, and extent. They can also help the study at the network level as well. So we are done with the literature review. So these slides basically give you some idea about a comprehensive framework we developed for improving bottleneck analysis. So we start with the defining of performance measures for freeway bottleneck analysis. And then we're going to apply those performance measures and also using the data we collected to identify and rank freeway bottlenecks. And then we're going to go on field trips to observe whether the data-based approach really provide information that they're convincible, they're really objective enough. So we go on the field trips and to validate the results. And then we're going to calibrate and validate a base DTA models. We also use the model to evaluate those improvement projects and evaluate them and rank them as well. So that's the framework we developed. So these slides basically discuss about the principles considered in past. So as you can see, figure 1, the left side. So historically, over the average has been communicated to the management when they make a decision. But as a traveler, we are, experience the congestions, in a dynamic manner. So what do you mean by that? So basically, this is a 24/7 issue. It's changing within the day and also from day to day. And these slides give us a list of potential performance measures that we can use. For example, the travel speed, travel time index, planning time index, buffer time index, and the CV, and also congested hours, V over C ratios. All these performance measures have been used by different researchers in different studies over the years. So we classify these performance measures into two big categories. First one we call is a reliability measure. So as you can see here, we have 4 different MOEs. The first one is the frequency of congestion. The second one is a planning time index. And then we also have BTI and CV. BTI and CV, in the next couple of slides, you're going to see that they're not suitable for use in our research. And you will see the reason why. And then the next category is intensity measures. So we have a travel time index, average travel speed, and also average travel time. And then we're going to use these performance measures to, in our research, we use the reliability measures first only. And then we also use the combined reliability and intensity measures to compare, to see different results as well. So these slides basically give you an idea, from different roadway segments in terms of different PTI values. So these slides, you're going to see BTI and CV. As you can see here in the equation, the way we calculate the BTI, the way we calculate CV measures, both use the mean travel time in the denominator. As we all know, the mean travel time itself is changing over the years due to the roadway improvement projects, due to the seasonal factors and constructions, variations in travel demand, all those activities going on over the years. So the mean travel time itself is a varying benchmark. So as a result, the BTI and the CV are also changing. We cannot use them if we are trying to see, we're used as a measure to compare against. They're not suitable. So these slides basically give us a flow chart of how to identify and rank freeway bottlenecks use a frequency of a congestion. So when we use 60% of the free flow speed as the threshold to compare, so these slides basically give us some pictures about AM peak period, PM peak period, and also AM and PM, both peak time periods. So as you can see from the last slides, so generally commuters experienced more frequent traffic congestion on freeways during PM than AM period. Second bullet here trying to convey a point, which is the traffic congestion on freeways is a directional pattern during both AM and PM peak periods. The last bullet trying to show this, which is some traffic management channel segments are heavily congested during both peak times. So during the bottleneck ranking and mitigation process, they should deserve a higher priority. And then these slides basically use the planning time index, 95th percentile travel time for the calculation purpose. And these slides all combined, the last 3 slides, basically we compared when we use 60% of the free flow speed. 75% of the free flow speed. The FOC 60 versus FOC 75, about 85% of the congested roadway segment are identical. We also use different threshold to calculate the PTI. For example, we use 80% percentile traffic time, also 95 percentile traffic time. Then about 80% of them are identical. We also compared FOC versus PTI. About 80 to 97% of the top 30 TMCs identified are identical. So what that says basically, the FOC or PTI, whatever is convenient for us, we can use either one. And also the percentage-wise, 60, 75% for FOC or 80, 95% traffic time, they're almost identical, to a significant part. And then the implication is FOC and the PTI both are classified as the reliability measure. These will only reveal a specific aspect of the distribution. And we must combine it with the traffic intensity index as well. So these slides basically give us some pictures about the intensity and reliability. As you can see here, the x-axis is PTI, which is the reliability measure. The y-axis is TTI.
This is Peter Lee from University.
Travel time index.
So we ordered a track.
As you can see here, using the red picture.
We ordered APC controller.
PTI.
And also Jason All told me it was shipped a few weeks ago, but today I checked.
So it should be good, huh? Here. So we use as an example here PTI. So this basically is the same reliability measure, but totally different intensity measure here. Likewise, for these two roadway segments, we have the same level of congestion, but the reliability is totally different between these two roadway segments. So we're going to use these two roadway segments as an example. Now, these two has the same reliability measure here in the next slides here. Okay. So these two roadway segments, as you can see, the reliability is almost the same, but the average speed is totally different. The average speed can be translated to the travel intensity. As you can see, we have the same reliability, level of reliability, but totally different level of congestion here, as you can see. So this slide clearly shows that we must combine both reliability and intensity measures when we identify bottlenecks. Okay, so we know that we must combine both dimensions. So we use PTI and TTI here in these slides and also in our research. The reason is very simple, because both measures use free flow traffic time in the denominator. So we can do some calculations. So we have an equation here called congestion ranking index, RI, equal to TTI plus gamma times PTI. So gamma is the weight assigned to the reliability dimension. So we have congestion ranking index equal to the intensity plus the weighting factor times the reliability. So that's the big picture. So we're moving on to the next slides here. So the weight is defined as the ratio of RR to the free flow traffic time on roadway segment I. So the ratio reliability itself is defined as the value of travel time reliability to the value of travel time. So that's how we define the RR. So why we define this way, we did a trick here. As you can see, we can start from the end all the way to the top. So the congestion ranking index here equal to, again, TTI plus the weight times the reliability. So as we all know, the travel time index equal to average travel time divided by free flow travel time. Plus, so if we define RR this way, we can just plug in 1 over free flow travel time times the value of travel time reliability divided by value of travel time times PTI. And if we do some manipulation, here we can get the numerator as VOTT times travel time plus VTTR times PTI. And the numerator will translate to the total travel time related cost under congested travel condition. And denominator will be equivalent to the total travel time related cost under free flow condition. As you can see here, the numerator is calculated under the congested travel condition. The denominator corresponds to the free flow travel condition. So that way we can calculate the ranking index. So here's the flow chart. I'm not going to go into all the details, but you're encouraged to see our technical reports and also our papers if you're interested. So we combine TTI and PTI into our equation. So we use the combined performance measure, PTI and TTI. We get some results here. We want to show you here. And then in terms of how to rank the freeway bottleneck, so we have the RI calculated for each roadway segment, and we're going to combine them into a group. We rank the freeway bottleneck group weighted by the vehicle miles traveled. As you can see the equation here, the RI is calculated for each roadway segment during maybe a particular month. And then we're going to sum them up across the time dimension, across the spatial location dimension as well. So time and space, we have 2 dimensions here. Also weighted by VMT. So we get the results for the AM peak periods here in these slides. So we get a lot of results based on the data analytics approach. So all these coming from data analysis perspective. So are they reliable? Are they good enough? You know, how much confidence we should have relevant to those results? That's a big question mark. So what we did next is this. So we went on several field trips to validate, to see whether the bottlenecks we ranked as, you know, top 30 or top 100, they're really congested, and how severe they are, and whether the locations are true, the times are true, and things like that. So we went on several field trips to observe. And these slides basically give you you know, picture of what we did in the past in our research project. And then we validate the results, you know, through several field trips. And the next step is, you know, how to use the result, how do you combine the field trips into, build them into our model. So this step basically use the DTA model. We're going to calibrate and also validate a base DTA model. So we use the Charlotte DOT and also Charlotte Regional Transportation Planning Organization model for the development purpose. We also get the AADT from the NCDOT website for the calibration of our OD metrics. And then we also use the critical route travel times coming from the INRIX data for the model validation purpose. As you can see here, we use the entire network, and then we use sub-network for calibration purpose as well. And we conducted several test runs in the model to calibrate the OD. And we use the built-in OD MEE, which stands for Origin to Destination Matrix Estimation Tool. As you can see, the R-square value improved significantly. And then we also validate the model using the route travel time. We have data from INRIX data. And we also validate the results. So basically, as you can see here, for a I-77 northbound, we have 4 minutes. I-70 southbound, 3.7 minutes or so, calculated as the root mean square error statistics, so which is about a 10% deviation from the route travel time, which is pretty good. Okay, so we calibrate the model. We know that we have a good DTA model. We can be fairly confident that we can trust our DTA model. So the next step is how to apply the DTA model. We calibrate, we validate it already, to evaluate our roadway improvement projects. So based on the field trips, we also design several scenarios in terms of how to improve the bottlenecks. So mainly we're coming from 2 perspectives. One is lane addition in terms of construction, the capacity addition. The second one, talking about road pricing. So how to charge people and see the impact R, and then we can evaluate the combined strategies. So that's the point here. And in terms of lane addition only, we have multiple scenarios. We have different strategies proposed to mitigate the freeway bottlenecks at different roadway segments. And we evaluate them in terms of different performance measures. And this basically, this slide is talking about the results. As you can see, the first one says, adding an extra lanes may improve network performance. For example, under scenario 11, we add 1 more lane. That capacity addition will improve network performance for sure. Some other scenarios though, we find that we cannot improve network. Instead, the network becomes worse than before. For example, scenario number 4, when we add another lane, the network actually becomes worse than before. As we all know, the brace paradox. Sometimes when we make decisions based on our engineering judgment, the decisions may not be optimized. So in those cases, our intention is trying to improve the network, but we end up with a network worse than before because of the existence of the brace paradox. We validate results. We see that clearly. The paradox does exist in our research project. The third one, talking about hidden bottlenecks. So when we mitigate the bottlenecks, when we build adding more lanes, initially those bottlenecks will be gone after the treatment. But we see that initially some bottlenecks are inactive, they're not there, you cannot see it. And after the bottleneck treatments, the inactive hidden bottleneck will emerge as the new bottleneck. For example, some of them are downstream of the treatment points. So what are the takeaways? So we as the transportation decision maker must be very careful in terms of making decisions. The decisions better be optimized in terms of adding more capacities. That's the point here. Otherwise, we may end up with a network worse than before, even though our intention is trying to improve the network. So the next couple of slides talking about the road pricing strategy. So we evaluate 15 roadway pricing scenarios. We clearly can observe the shifts in driver route choice. So people will switch routes in order to improve their traffic times. And then we propose different strategies combining road capacity addition and also pricing. The next step would be how to evaluate them, how to rank them. So here's the framework. Step one, we develop different projects as candidate solutions. We're going to evaluate each and every one of them, and we're going to screen them in terms of, if some networks are worse than before due to the implementation of some projects, then we will not consider those projects in terms of screening. And then step 4, we conduct benefit cost analysis. Step 5, we will conduct sensitivity analysis as well. So again, we screened several projects. If the improvement projects actually produce a worse network than before, then we will simply not consider them at all. So inside the box here, we have projects that improve the networks. Then we will consider them as candidate solutions. And then next step is trying to conduct benefit and cost analysis. So as you can see here, we have different scenarios after the screening of the projects. In other words, we have several projects that can improve the network performance. For those projects, we're going to list them here. And then we're going to see the construction mileage. After conduct a comprehensive review of the literatures, we're going to see the approximate cost in terms of congestions. On a per mileage basis, we can calculate the total cost. We can also calculate the operating and maintenance cost, typically as a percentage of the construction cost. Typically the researchers assume 5% of the construction cost as the OM cost. And we will conduct sensitivity analysis as well by varying this percentage-wise from 1 to 5 to 10%. And then we can also calculate the total cost, the total benefit in terms of travel time or cost saved. And then we have benefit divided by cost, benefit cost analysis ratio, and then we rank them based on the calculations. And then these slides talking about the result here. So 17 out of 18 projects generate higher benefits as compared to the project cost. In other words, the benefit over cost ratio is greater than 1. The only exceptions is project 21, in which B over C ratio is less than 1, which indicate the project is not economically feasible at all. And the second bullet, so lane addition project generally result in high benefit over cost ratios. We have 3 different scenarios, for example, 11, 18, and 25. And then we also have some road pricing only, and also combined strategies. They also have a very high B over C ratio as well. In this project, those low-cost capacity expansion projects are highly recommended because of the high B over C ratio. Again, we also conducted a sensitivity analysis here in our study in terms of the percentage OM cost, in terms of construction cost per mileage basis, also the construction cost of adding a general purpose lane as well, again, on a per mileage basis. And the result shows that they are pretty consistent in terms of the different assumptions. And we also show that the scenario 11 and 18 are highly, has high B over C ratio. So they're highly recommended for mitigating bottlenecks in our study. Now, this slide talk about a contribution of our research study. So we define a set of MOEs that can be used, that are suitable for use in identifying and ranking freeway bottleneck analysis. And then we evaluate and compare them in different scenarios. For example, we found that FOC and PTI both are pretty good, and they're also almost equivalent. And we also use different threshold values to compare. PTI, we use different percentile traffic dam. For FOC, we use different percent of free flow speed as well. And we compare them, we get some results that are pretty good. And then we also developed a systematic approach for ranking and identifying and ranking those bottlenecks using both reliability and intensity dimensions. We also conducted a case study in the city of Charlotte area. We calibrate and validate DTA model. We verify the existence of a brace paradox and also hidden bottlenecks. We also ranked the roadway improvement projects as well. So that's pretty much present a framework that we developed, the result we obtained here. In some technology transfer activity in the past, we have 2 papers published in JTE that are directly related to our research. And then the 3rd, 4th, and 5th bullet shows the research that we conducted. We applied the research into our future research as well. The last one, we also applied the framework into the rail transit network, and we just got accepted for publication in actually 2 or 3 days ago. So this slides talk about technology transfer activities. So if you have any questions, I'll be happy to take, or I can see here. If any of you have any questions here. I did not see any questions. So if you have any, just send me back, a message here. I'd be glad to answer. Otherwise, you're more than welcome to contact me, via email. And my email is wfan7@uncc.edu. So that's pretty much wrap up my presentation. Thank you very much for attending the webinar. We appreciate your time and hope that you will continue to stay safe and healthy. Thanks again.
Thank you, Dr. Fan.
Thank you.
Thank you, Dr. Fan.